Okie dokie. Now we're going to start part 3 of this, and we're on problem number 21. Problem number 21 says a 90-kilogram skydiver hanging from a parachute bounces up and down with a period of 1.5 seconds. And his mass is 90 kilograms. And I'm going to put ones there just in case. What is the new period? So there's another period here. If the second skydiver comes along, whose mass is 60 kilograms, hangs on the legs, and you can see it here how it's set up, his mass is 60, but M2 is going to be 60 plus 90 or 150 kilograms. Okay, so we're in the same situation. T1 over T2 is going to equal the square root of M1 over M2. And another way to do this, rather than do all the rearranging with letters, is just put the numbers in, which is what I did on this one, just for the heck of it. So 1.50 over T2 is going to equal the square root of 90 over 150. And if you just do the math here, you can do this division and then take the square root of it. Then it's going to be, the t will come over here, and then you end up dividing 1.5 by that. And T2 comes out to be 1.94 seconds. Okie doke. The next one is problem number 22. Now with problem number 22, we move into a new set of problems. And the key equation, the new equation that's introduced here, is the period is equal to 2 pi, but instead of m over k, it's now L over g, where g is gravity, and as it says here, it's 9.80 meters per second squared. Now the interesting thing about this is that with the pendulum movement, the mass of the pendulum, the weight that's on the pendulum, has no effect on the pendulum's period or frequency. And a lot of people intellectually sometimes have difficulty understanding that or grasping that. The first question here is, what is the length of the pendulum that has a period of 0.5 seconds? So we basically solve this equation for length. So we end up with t over 2 pi. We take that squared, and that ends up giving us L over g. And then we multiply this by g, or squared here. We multiply that by g, so we get t over 2 pi squared times g is equal to L. And now we put our numbers in. We get the period here for this problem is 0.5 seconds, excuse me, 0.5 seconds. And 2 pi here, and then the 9.8 equals L, and L is going to be, if you do the math here, is 0.0621 meters, because g is in meters per second squared. Okay, and so that's going to be 6.21 centimeters. 7 is the next problem. 27 states, 2 parakeets sit on a swing with their combined center of gravity 10 centimeters below the pivot. So L is going to be 10 centimeters, which is 0.100 meters. And I'd suggest, so you don't get units confusion that you change things to meters in this problem because gravity is always in meters per second squared. And so it says, what is the frequency of the swing? Now, if you do this, you say T is equal to 2 pi square root of L over G. Well, what you can do here is remember that T is 1 over F. So you can change this equation to that F is equal to 1 over 2 pi square root of G over L, if you want to. Or you can just do it and find the period and take the inverse of that. Either way, if we do this, which is the way I did it, you get 0.1 and 9.8. You do the math here, you get 0.6347 seconds. You take the inverse of that, 1 over, you take the inverse of that and you get 1.58 hertz. And that's the frequency. Number 28. Number 28 states, a pendulum has a period of 3 seconds. Now you notice that it has a lot of zeros, and there's a reason for that. Because we're going to make very small changes. The gravity G1 is now going to be 9.79 meters per second squared. When you see this kind of thing, you got to be suspicious that they're going to do something with gravity, okay? It's moved to a different location where a new gravity, G2, is going to be 9.82. What did it just do? 9.82 meters per second squared. Okay, so the question is how much does the period change? Well, we have a situation that's one of these T1 over T2 things. T1 over T2, we'll put the whole thing in here because it's the first time we've done it with this one. L over G1, 2 pi square root of L over G2. This stuff cancels out, this cancels out. What you end up with is the square root of G2. So if we put that in here, 9.79 and 9.82, we find that if we work it out, we find that T2 is now going to equal 2.9954 seconds. So it doesn't change it very much. And that's one of the reasons you need all these figures. And that's what the next question is on the thing is, why do you need so many digits? Well, if you have a 1% change in G, because you end up changing L, the L or the T, in this case, is going to change by a factor. Remember, we're talking percentages here. So it's going to be 0.01 is a 1% change in G, but that's going to be squared. So the delta T change is going to be 0.0001. So you need that much significant figures in order to be able to do the problem. I'll leave that like that so you can see it. Okay, problem number 30 is more of a conceptual problem. I'll go through it very quickly. It says, what is the effect in the period of a pendulum if you double the length? Okay, the relationship between period and length is the change in period is affected by the square root of the change in the length. So if you look at the ratio of 2L over L, it's going to be the square root of that is going to be the ratio of t over t. And the L's cancel out, so that if you double the length, you increase the period by the square root of 2, or about 1.4. The second question is similar. It says, can't read it. What is the effect on the period of a pendulum if you decrease the length by 5%? So instead of doubling it, you decrease it by 5%, but still what's going to happen is it's going to be the square root of a 5% decrease. So it goes from 1 to 0.95. So it's going to be the square root of 0.95. So the period will decrease by the square root of 0.95, which ends up being 0.974. It decreases by a factor of 0.974 of the original t. I don't particularly like to put problems like this on quizzes, tests, so you don't really have to. I mean, but it is nice to conceptually see what happens with certain changes. The next problem, number 33. Suppose the length of a clock's pendulum is changed by exactly 1%. What time will it read 24 hours later? Okay, there are two answers because you can change 1%, you can increase the length by 1%, or you can decrease the length by 1%. If you remember how clocks, like grandfather clocks, are designed, they look like this. Okay, and you have a pendulum in the middle here, and there's a weight. This is not a very good drawing. And the way you adjust your clock, if it reads fast or slow, is you move this up or down. So, if, for example, you notice that the clock is running a certain amount fast, you can actually use this kind of calculation in order to tell how much to move this weight in order to fix it. Okay? So, let's take, for example, you have two periods. Okay, the first one is it's running properly. The second one is with the change of 1%, so it's going to equal to L2 over L1 square root. Okay, so in the first case, if you lengthen it, if L2 is 1.01 times L1, then, and it's the square root, the L1's cancel, and so the change in period is the square root of 1.01. And conversely, if this goes down, then the change in period is 0.99. In other words, if you shorten it by 1%, then the number in here will be 0.99, and the difference will be the square root, the effect on the period. So that means that T2 in the first case is equal to T1 times the square root of 1, which is 1.00499. So it changes by this much. And so if the original is 24 hours, then the new is going to be 24 times this for the next 24 hours, which comes out 24.12. Conversely, you put in the square root of, so T2 is now going to equal T1 times the square root of 0.99, which is 0.99499, and it's going to be 23.88. So that's the impact of changing by 1%. And you can figure out how much 0.12 an hour is if you want to. The last two problems are not the kind of problems I would put on a quiz or test because they're challenging to think about. But I thought I would include them because I think they're interesting. These are the combine the idea of harmonic motion and energy. And so you have to take into account the energy impact. And I'll show you how that works in just a minute. So let's do number 35. And then I'll leave number 36 for you guys to think about and work on. And if you want to ask about it in class, we can do it. So a length of rope, which a mountain climber is suspended, it has a constant. They give you the constant in this case of 1.40 times 10 to the 5th, or 4th, excuse me, newtons per meter. What is the frequency at which he bounces given his mass plus the mass of his equipment is 90 kilos? So he's on this rope. So what frequency does he bounce? So F is equal to 1 over 2 pi square root of K over M. We put our numbers in here, we get 1 over 2 pi square root of 1.4 times 10 to the 4th divided by M, which is 90 kilograms. We do the math here and we get 1.99 hertz. So the frequency is 1.99. Now the second question is, how much would this rope stretch to break the climber's fall if he free falls 2 meters before the rope runs out of slack? Hint, use conservation of energy. Well, what you have here is you have the potential energy generated by a fall of 2 meters. And we remember from our old potential energy that that is equal to mgh. If you put the numbers in, you get an energy that's generated by that of 1,764 newtons, or joules, excuse me. So that's the energy of a climber falling 2 meters. But the elastic energy is equal to 1/2 kx, where x represents the amount that it would stretch. So 1/2 k x squared is going to equal 1764. So that means that x squared is equal to 2 times 1764. You multiply this by 2, divided by 1.4 times 10 to the 4th. And that's x squared. So x is going to be the square root of that. And if you do the math here, you get 0.502 meters. That's how far it stretches in order to absorb the energy generated by that much of a fall. Now part C, it says repeat both parts of this problem in the situation where twice the length of the rope is used. I'm not sure, I didn't do this part, and the reason I didn't do it is because I wasn't sure if that meant that the person falls 4 meters. I'm not sure what it means, because if you look at this equation, the length of rope doesn't matter. It has the same frequency, okay? So the only change here, you have to think, are they saying that he falls 4 meters? Because there's no length here. There's x, but x is the change in length that is absorbed. It's not affected by the length. So I just didn't do the second part, or that part C, because of that. And like I said, I've worked this out, but I'm going to stop here and say we're done for the day. And if you have questions about number 36, we can go over that. Now I want to thank you for your time.